I'd like to briefly review definite integrals. And I really want to look at two examples here. And the first example is essentially going to be taking the definite integral in general. And the second example, the one on my left here, will actually leverage some integral properties, definite integral properties, which will essentially help us solve this particular question here. So the first question, it's important for us to make a distinction between what it really means to find a definite integral versus a indefinite integral. In an indefinite integral, the interval of a particular function is undefined in the sense that it is not explicitly stated. So here, if we had a particular function and we were told to find the area under the curve, we're not actually bounded by an interval, as opposed to actually being bounded by an interval, where we would have something of the form that sort of resembles this. And in this case, in this particular case here, we could imagine the interval as being 1 to 3, where 1 is the lower bound and 3 is the upper bound. So the definite integral is essentially finding the area under the curve of a specific, particular, defined interval, as opposed to indefinite integrals. Now, we essentially want to solve this question by first finding big F, f of x, which is actually the antiderivative of the function that we have as our integrand. And essentially the idea of big F, and let me go ahead and write this off to the side, is that so the big idea here is that f of x, and of course this is big X, is the antiderivative of f of x, which is little x, if and only if the first derivative of f of x, which is supposed as being the antiderivative, is in fact the original function. In other words, I want to essentially find a function whose first derivative is the original integrand. And so that's really what it means at the heart of it, to find the antiderivative. But to solve this particular problem here, where we're finding the area under a curve, which is of course defined in a particular interval, we find the antiderivative first, which is a sort of the reverse of finding the derivative. And here it would just be a matter of using the reverse power rule, which would essentially be we would essentially add 1 to the power over that particular power, plus 2 multiplied by sort of the same logic here. And I'm going to write this as x squared, since our 2's would essentially cancel out, minus 4x. With definite integration, we actually don't include the plus c, the constant of integration. And much of that has to do with the fundamental theorem of calculus, part 2, which essentially cancels out the c's in terms of algebra. And I think we'll explore that later on. But for now, I think it's enough to understand that the antiderivative of this particular function here is, in fact, going to be what we've arrived at. And you can think of this as, again, being the antiderivative if and only if the derivative, the first derivative of this, in other words, if I were to put a Lagrange notation here, the first derivative of this should essentially lead me back to the original integrand, the original function that I was finding the antiderivative of. And we can sort of understand that this may be the case because we have our second term as being 2x in our original function, and in our antiderivative we have it as being x squared. If we were to take the derivative of x squared, we would essentially move the power out to the front and decrement the power by 1, and we'd essentially arrive at 2x, a term which is also found in our original function. Similarly, with the last term here, minus 4x, to sort of take the derivative of this would essentially be to leverage the derivative rule, which states that the derivative of a constant multiplied by a function is but the constant multiplied by the derivative of the function, which we know that the derivative of function x is just 1, which would leave us with 4, something we also find in the original function. So we have a good understanding that this particular function is in fact the antiderivative of the original function. And now what we'd want to do is we would want to take or we want to evaluate this particular antiderivative for the region of 1 to 3. So we would do this by plugging in 3 into our upper bound into this particular function here. And we would also essentially plug in f of 1, and we would subtract later on, we would subtract f of 3 or f of 1 from f of 3. In other words, algebraically, in a general sense, if you were to find the antiderivative and then evaluate it for the limits here, you can consider 1 and 3 as being perhaps b and a, where after you would plug in f of a, or you would plug in a as an input into the function that you found, which is of course the antiderivative, and you would essentially subtract from this the same thing, but with b as an input. And the answer of that would essentially be the area under the curve. So that's essentially the same line of logic that we're essentially abiding by here. And we can first do this with, we can first plug in f of 3. And doing so, we would get 3 cubed at the top over 3 plus 3 squared minus 4 multiplied by 3. Now, of course, this would be, well, it would be 27 over 3 plus 9 minus 12. And this would essentially simplify out to being 9 itself. So we would essentially be left with having 9 plus 9 minus 12, which seems to be 18 minus 12. Which would be nothing but 6. So for our f of 3, so let's just go off to the side and make a small note here that our f of 3 is in fact going to be equal to 6. And of course, we would want to find f of 1 as well, which would be our lower region. F of 1 would essentially be the antiderivative with the input 1. So it would essentially just be 1 cubed over 3 plus 1 squared minus 4 times 1. And of course, this would be 1 over 3 plus 1 minus 4, which I guess we could separate this as being 1 over 3 plus 3 over 3 minus 4, which would come about to being 4 over 3 minus 4 over 1, which we could think of as being this here, which we would get as minus 8 over 3. So we would essentially, given that we wanted to subtract f of 3, which is equal to 6, and f of 1, which is equal to negative 8 over 3, we would essentially get something like this. And of course, this would come about to being the addition of this particular problem, which would come about to being 18 plus 8, which would be 26 over 3, which would be our final answer. So this is a rough idea of actually how to find the definite integral, but it gets a little more complex with problems like this. So knowing now that this will be a subset of, this will be a part of a bigger problem, let's move towards the more complex problem type and sort of work through it with proper logic. So the idea here is to understand really what we're dealing with. We are told to find the area under a curve or the antiderivative of cosine of x on a particular interval, which is negative pi over 2 to pi over 2. And the idea here is to first understand that we have this idea of a function either being odd or even. And these are two different integral properties. So let me go ahead and first cover the first type and then of course the second type. So the first type is really just saying that it's your even integral property, even if your function, if your integrand is even. For instance, if we had something like f of x squared, and you had it from the points of -1 to 1, your graph would essentially look something like this. Well, we know that x squared is in fact it's a parabola. And the idea here is to understand that it's asking us to find the area under the curve from -1 to 1, which would in fact be this particular region right here. So I think one thing we can definitely deduce is that the area is essentially the same on both sides. So you can think of this as being, for instance, the area here would essentially be symmetrical to or equal to the area here. So the area on the right would be symmetrical to the area on the left or equal to the area on the left. So is there any way for us to essentially symbolize that fact without having to essentially consider the whole interval? Well, there is. If we only consider the right interval and multiply the area of that or the antiderivative of that by 2, we would essentially get double the area, which is of course what we would expect. So for an even function on a particular interval resembling this, for instance, if you had to find the antiderivative of a to, or negative a to a of a particular function which is even, then this would essentially equal 2 multiplied by f, or not f, but the antiderivative of that particular function, which is of course, which is even from the interval 0 to that particular interval. So in this case here, we don't actually need to find the interval from, we don't actually need to find the area under the bounded region from -1 to 1. We can just start looking at the interval from 0 to 1. So we would and multiply that by 2. So we would do 2 multiplied by not f, but the integral from 0 to 1, since that's what our a is, of x squared dx, which of course we would then find f of x, capital F of x, big F of x, which would be the antiderivative of this, which would of course be x3 over 3, and we would multiply that by 2, which would give us 2x 3 over 3. So that is essentially the property for even functions, where if we had if we were told to find the antiderivative on a particular interval from negative a to a of a function which is even, then this would essentially equal to 2 multiplied by that by the antiderivative on the interval 0 to a of that particular function, and that would essentially be the area um, of the bounded region, or that would be the antiderivative. Now, with the odd functions, it's a little different. So let me go ahead and cover the odd functions. So with the odd function, it's a tad bit different because, for instance, if we had to find the antiderivative of let's say x to the third dx, the graphical representation of which looks something like looks something along the lines of this, we would find that negative 1 would start from here and it would essentially end here at 1. So this is essentially our interval here, and you could understand that the area under the curve, while it is symmetrical, it seems to cancel out on itself. And the idea behind that is, if you remember geometrically, the way we would essentially find the area under the curve was to essentially break apart the area under the curve into several rectangles, and then actually add all those rectangles to each other. So if you were to zoom in onto this particular area here, if you were to get a bigger version of what I have in this particular quadrant, in order to find the area here, you would essentially break this up into a bunch of rectangles, and you would essentially add those rectangles to each other, and that would essentially, you would integrate them in a sense, and that would essentially be your area. Now, what you're actually doing is you're finding the area of a particular rectangle, and then adding that with the area of all the other rectangles. So recall that to find the area of a rectangle, you do base times height. And of course, the base times height in this particular quadrant, if you were to think about in the first quadrant, that is, you would evaluate your height on the basis of what your y value is. And then, of course, you'd evaluate your width on the basis of, or your base, you would evaluate that on the basis of what your x value is. And so your x value times your y value in the first quadrant would in fact be positive. And so so if we had, let's say, positive a as symbolizing the addition of the areas of all the rectangles we had in the first quadrant, added to the area of all of the rectangles that we had in what seems to be the third quadrant, because we're actually going counterclockwise. So the third quadrant being here. So if we were to add that to the rectangle, or the area of all the rectangles, we would find the rectangle by the base times the height. Now the base, in this particular case, that is of course the x value, would be negative, whereas our height would also, or the y value would also be, would essentially also be negative. And of course, adding a negative to a negative would essentially get us a negative. So we would have, let's have a symbolize the area of all the rectangles we have in the third quadrant, which would be negative. And then of course our negative would just cancel out with our positive, and so we would just be left with 0. So we have an understanding that that for a particular interval for an odd function, from negative a to a, or in this case negative 1 to 1, as being a manifestation of negative a to a would in fact end up being 0. So with that in mind, let's see which we can leverage here. So it seems as though we're dealing with cosine, and we know that the graph of, well, we know that characteristically cosine is in fact a even function, and it looks something like this here, kind of like a horseshoe. And of course, this would be one period of the cosine graph, and where it intersects with the x-axis here can be thought of as negative pi over 2. And of course, where it would cross the x-axis here is pi over 2. So really, it's asking us for the interval, the area under the curve on this particular interval here. So really, you can think of this as being the area of simply this part of the cosine graph, from negative pi over 2 to pi over 2. Now, we have an understanding that cosine is an even function. And so if we recognize what we just learned about even functions, even functions on the interval of negative a to a, or in other words, if you think about it like this, you have negative a to a of an even function, which is cosine of f of x, or let's just say f of x here, would essentially be equal to 2 multiplied by 0 to a of f of x dx. So really, we're looking for the antiderivative of f of x, which in this case is cosine, on this particular interval. So really, we can think of this question as being finding the antiderivative of cosine on the interval of 0 to pi over 2 cosine x dx. So this is essentially how we've rewritten our answer, or our question rather, our problem statement. And of course, this makes sense because you understand that the area under the curve on this side is essentially equivalent to the area of the curve on this side. So just finding the area under the curve on the interval 0 to wherever this takes us, which is in fact pi over 2, makes sense. And then of course multiplying that by 2. So we have to do that here as well. Will just be double the area of the curve we have here, which again makes geometric it makes geometric sense. So 2 multiplied by f of 0 on the interval, or find 2 times the antiderivative of cosine x on this particular interval would essentially be a question of finding the antiderivative of cosine x, which we know is sine of x, and then multiplying that by 2. And then, of course, as we mentioned before, we will evaluate for this particular region. So we want to essentially do 2 multiplied by, well, we want to think of it this way. We want to take the antiderivative, big F, and essentially plug in the upper bound minus that from the lower bound. So if I were to plug in the upper bound into this particular function, that would just be a matter of multiplying 2 by sine of the upper bound, which is pi over 2. And if I wanted to plug in, or if I wanted to evaluate the lower bound, which would be 0, then I could plug 0 as an input, multiply 2 by sine of 0. So 2 times the sine of pi over 2. So if we think about our unit circle here, pi over 2 is in fact equivalent to 90 degrees. So we know it's a quadrantal angle. And pi over 2, or rather, since we know that sine is in fact referring to y, sine of x refers to y, and cosine of x actually refers to the x, we're actually asked what the y value is at pi over 2. So the y value at pi over 2 would in fact be 1, given that this is a unit circle. And the y value at 0 degrees, which would in fact be here, would in fact be 0. So if we were to do 2 times 1, we would essentially get 2, and we would minus that by, so it would essentially be 2 times 0, or actually 2 minus 0, which would essentially be 2, which would be our final answer.